Today we're going to talk about exponential and logarithmic equations. These are properties we've talked about before for any a greater than 0 and not equal to 1. If a to the x equals a to the y, then x equals y. And for any m greater than 0 and n, and a greater than 0 and a not equal to 1, log base a of m is equal to log base b of n, then m equals n. So basically saying if you have the same thing on both sides, we can ignore the bases and set x equal to y. And if you have the same base on each side of your log, you can ignore them and just set m equal to n. Alright, with that in mind, let's solve this equation. Well, there are a lot of different ways I can do this, but I know that 27 is a power of 3. 27 is 3 times 9, which is 3 times 3, so it's 3 cubed. And so 3 to the 2x minus 5 equals 3 cubed, and because of the same base and this rule up here, I can now ignore these and set this 2x minus 5 equal to 3, 2x equals 8, or x is equal to 4. Alright, so this one says solve this equation, find the exact answer, and then approximate it to 3 decimal places. So I'll point out what the exact one and then the approximate answer is. So what I don't like here is this is 3 here, so I'm going to divide both sides by 3, and I get e to the x plus 2 is equal to 8. Okay, so, well, my variable's trapped up here in the exponent, but I know if I take the natural log of both sides, then that power rule can bring that down. So the natural log of e to the x plus 2 equals the natural log of 8. And that becomes x plus 2 is equal to the natural log of 8. And then I can subtract 2 from both sides, and I get x is equal to natural log 8 minus 2. So that would be your exact answer. And to approximate it, we're going to put it in the calculator. So I'll bring this out here, clear my screen. And so I do the natural log 8 minus 2, and I get 0.794. So x is approximately 0.0794. So this is your, oh, it says 3 decimal places, so the 4 doesn't need to be there. That's why it's always good to look at your problem and make sure that you're answering what they asked for. And this is your approximate answer. Alright. See if I can make this line up a little bit better. Okay. So that's just another this is reminding you of the definition of a log, and this is reminding you of the property from the last page. So I can rewrite this as an exponential function and write this as 3x minus 5. Remember, think about this coming over here and bumping this up. So equals 2 to the 4th. And 2 to the 4th. Oh, that's horrible. It's going to be a bad handwriting day. I'll try to do better. Okay, so this becomes 3x minus 5 equals 16. Add 5 to both sides, I get 3x is equal to 21, or x is equal to 7. Now, logs have a domain restriction, so it's always kind of good to go ahead and check your work, even though this one looks like it's going to work. You just got to make sure that you are that this is not a negative number, but since it's a positive number, we know that this answer works. Okay, so let's solve this. Well, gross. Let's see, maybe we can, these are all log base 4, right? And I can put this into one expression because of the rules that we learned. So this is log base 4 of x plus 6 over 2x plus 5 equals, oh, that's a power, right? So that would be log base 4 of x to the negative 1. So this is log base 4 x plus 6, 2x plus 5 equals log base 4 of 1 over x. And now I have a log base 4 here and a log base 4 here, so now I can just forget about them. And 2x plus 5, and I have 1 over x here. And now I can solve this. I'm going to cross multiply this. Anytime you have a fraction equal a fraction, you can cross multiply. So I have x times x plus 6 is equal to 1 times 2x plus 5. So that gives me x squared plus 6x is equal to 2x plus 5. I'm going to subtract these over here, so I have x squared plus 4x minus 5 equal to 0. Factor this. X, 1, and 5. Want this to be positive, so the bigger number has to be positive. So I have x minus 1 equal to 0, x plus 5 equal to 0. So I have x is equal to 1 and x is equal to negative 5. So just looking at this, if I put 1 in here, that gives me 7. If I put 1 in here, that's 2 times 1 plus 5. So that's 7. So that's cool. I know that 1 will work. If I put negative 5 in here, well, that's negative 5 plus 6, so that one's okay. But if I put negative 5 in here, it's 2 times negative 5 plus 5, which gives me a negative 5, and I know I can't take the log of a negative number. So this is what we call an extraneous solution. So especially most solutions you should put back in anytime there's a domain restriction, but especially if you have if you've squared it and factored quadratic, sometimes you're going to have an extraneous solution, so it's always good to double check. Alright. Okay. For some reason, I don't know if I don't have this high enough. I'm running out of, just not getting the best view. Okay. So this is using the one-to-one property of exponential functions, saying if you have the same base, then you just set the exponents to equal to each other. So here I have same base, so I can just say x minus 1 must equal 2x minus 4. And I get negative 1 is equal to x minus 4, add 4 to both sides. And I get x is equal to 3. And then there's no domain restrictions with that, so we should be good here. Okay, well, that's gross. Let's see. I know that I can rewrite 8 as a base of 2 and 16 as a base of 2, so I'm going to go ahead and do that. 8 is 2 cubed. And 16 is 2 to the 4th. And so this becomes 2 to the 3 times x times 2 equals 2 to the 4th times x plus 1. Now that we have the same base, we can ignore this and get 3x plus 2 equals 4x plus 1. And so 3x plus 6 is equal to 4x plus 4. And subtract 3 from both sides. I get 6 is equal to x plus 4. Subtract 4 from both sides. And I get x is equal to 2. And I don't have logarithms, so I'm not worried about checking the domain. Okay, here this may look kind of tricky, but remember that square root is to the 1/2 power. So 2 to the 5x is the same as 2 to the 1/2 power. And I can ignore the bases now and get 5x equals 1/2. And then I can, so there's different things I can do. What I'm going to do is I'm just going to get rid of the fraction and divide or multiply both sides by 2. Because sometimes fractions make me nervous, or they used to. And so that gets me 10x. These cancel out, equal to 1. Divide both sides by 10. And I get x is equal to 1/10. Alright, so those are great tricks we can use under the same bases. There's no way that I can make 5 and 4 into bases that are alike. So we have to take the log or natural log of both sides to basically let these guys escape. So I get natural log 5x plus 2 equals the natural log of 4 times x. Use that power rule. And I get x plus 2 times the natural log of 5 equals x times the natural log of 4. I'm going to distribute that in, and I get x natural log of 5 plus 2 natural log of 5 equals x x natural log of 4, and then everything with x on one side, everything without on the other. So x natural log 5 minus natural x natural. Ugh, boy, my tongue is not working today. I am sorry. That is a minus. That's why I erased it in the first place. So what I'm doing is I'm subtracting this from both sides to get it over here. And then subtracting this to get it over here. And then this is, I can power rule this here. And so this side becomes natural log of 5 to the negative 2. And this is, I can go ahead and take out an x here, natural log 5 minus the natural log of 4. And then I come over here, this side becomes x times the natural log of 5 divided by 4 equals the natural log 5 to the negative 2 power is 1/25. And then all I need now is to get x by itself, so I need to divide both sides. And I get x is equal to the natural log of 1/25 divided by the natural log of 5/4. And it doesn't tell me to give it an approximate value. This is an exact value. It doesn't give me an approximate value, but if I were to put that in my calculator, it would actually give me a number. Alright, so question, is there any way to solve 2 to the x equals 3 to the x? Yes, you can do that if the solution is 0. You can also go to Desmos and put 2 to the x in, and 3 to the x, like two different equations. So y equals 2x and y equals 3x, and where they cross in Desmos will also be your answer, and that will be at the point where x equals 0. Okay, so let's look at this guy. So I don't like having 20 next to e to the 2t, so I'm going to go ahead and divide both sides by 20. I just want to get both sides as simple as possible before I start moving stuff around. So 5 equals e to the 2t. And in order, the variable is trapped up here, so in order to release it or let it escape, I need to take the natural log of both sides. And so I get natural log 5 is equal, these cancel out, to 2t. And and then I divide both sides by 2, and then get the natural log of 5 over 2. Now, if it asks for an approximate, you go ahead and put it in your calculator, that's fine, but they didn't ask for it. But how would you do that? You would hit natural log 5 parenthesis divided by 2. There you go. That's what it equals approximately. Alright, so I look at this and I go, it looks like a lot, but I can simplify it. Always try to get it as simple as possible before I start doing logs or moving stuff around, or doing crazy stuff to it. So I'm going to subtract 5 from both sides, and I get 4e to the 2x is equal to 7. And then divide both sides by 4, so e to the 2x equals 7 over 4. And I need to untrap this x up here, so I'm going to take the natural log of both sides. Can you use log? Absolutely. I'm just lazy and write natural log because it's 2 letters instead of 3 each time I write it. These go away and I get 2x is equal to natural log of 7 over 4. And then I want x by itself, so x is equal to natural log 7/4 over 2. Okay, this one looks like it might be a quadratic. Okay, so if you're like, I don't even want to do this, you could take this side, y equals e to the 2x minus e to the x in Desmos, and then make your second equation y equal to 56, and you can click on where these two where they intersect, and it's going to give you a decimal. It's not going to be the exact answer, it's going to give you the approximate, but if you are on a test, I would look and check for both that. Now your homework program might tell you you're wrong, but if you're like freaking out and you're like, I don't know how to do this, anytime you just, when things are equal to each other, you look for where they intersect. I'm going to always go, even if Newton Alto counts it wrong on a quiz or a test, I'm going to go back and double check and look, and if it's an equivalent form, I'm going to give you the point. So, but I'm going to go ahead and rewrite this. And factor it. And so I have 7 and 8, and e to the x, e to the x. And I want, this is negative, so the bigger number needs to be negative. So I get e to the x is equal to 7, or negative 7, excuse me, or e to the x is equal to 8. And take the natural log of both sides because I need to let this x escape. So the natural log e to the x is equal to the natural log of minus 7. Except I can't take the natural log of a negative number. And if you're anxious and you're like, well, I don't know, Amy, like, I'm taking this test and I don't know, can I do that? Do natural log negative 7, and your calculator is going to go non-real answer, and you'll know that you can't do it. So this is not an answer. Okay, that would be an extraneous solution. I remember I said sometimes when you factor things, you have a quadratic, you just have to double check that both work, especially when you have a domain restriction. Okay, I take the natural log of both sides of this, and I get x is equal to natural log 8, and that is my answer. So this says, sometimes we can rewrite, this is just reminding you of the definition of a logarithm. So I'm going to look at this like any other. I'm going to try to simplify both sides. And I get natural log, 2 times the natural log of x equals 4, but I'm going to divide both sides by 2. And I get natural log x equal to 2. And I know from my earlier, I can rewrite this, because remember this is log base e. And so now I know that E, the 2 equals X. I can do it that way. Because this comes over and bumps that up. Or I can come here and use a rule of logarithms that we got in a previous section, saying that if I raise both sides to the power of E, these cancel out, and I get X is equal to E squared. So that's totally up to you. Okay, choose your own adventure. Alright, let's look at another one. So I'm going to divide both sides. Let's see, what am I going to do here? I'm going to divide both sides by 2, because I don't like anything in front of the natural log, and I get natural log of 6x equals 7 over 2. And then, so I can raise both to the e power, or I can rewrite it by the definition. Let's rewrite it as the definition, because that's what it asked me to do. So e to the 1/2 is equal to 6x. That's 1/2. That's a 7/2. And then I'm going to divide both sides by 6. And I get x is equal to e to the 7/2 over 6. And so that's the precise answer. If they want approximate, then you need to put it into your calculator. Okay. So anytime I have the same log on both sides, these are both natural log, I can ignore them. And I can write this as x squared is equal to 2x plus 3. I have a squared, so I know I need to go ahead and move everything to the other side and solve for 0. I'm going to factor this. I have 3 and 1, x, and I want this to be negative, so the bigger number is going to have that, and so I get x is equal to -1, or x is equal to 3. And let's check this. If this is 1 squared, it's positive. 2 times 1, -1 is -2 plus 3 is 1, so that's fine. And this is positive, so we know these are both fine. So they're both our answers. You just got to double check and make sure you're not violating a domain restriction. Alright, so here's an application problem. In a previous, one application we can do is in science is calculating the time it takes for a half of the unstable material in a sample of radioactive substance to decay, called a half-life. And it's in this table, lists the half-life for several of the more common radioactive substances. So these are the equations that you can use. A naught, or a sub 0, is the amount initially present. T, big T, is the half-life. Little t is the time period over which the substance is studied, and A of t is the amount the substance is present after time. And I did not give enough room down here. I apologize. So I'm going to start up here. How long will it take for 10% of a 100 or 1,000 gram sample of uranium-235 to decay? Well, it's up here. This is, of course, we get the big, most obnoxious number for this problem. So it says, how long will it take for 10? So we want to know, what is T, right? And 10% of 1,000 is 100. So we would say 1,000 minus 100 equals 900 left. And then our initial amount that we had was 1,000. And the half-life, big T, is this big obnoxious number. Alright, in years. So I'm going to go ahead and put it in this equation here. Why that equation? It's the, well, you could, that's just what I chose. Okay. So, so we already know, and this is actually A of T here. So we know 900 equals 1000 e to the natural log 0.5, that's from the formula, divided by the half-life, which is this big ginormous number, times what we're trying to figure out, t. And so if I divide both sides by 1000, I get 0.9 is equal to e natural log 0.5. I would wait. I would really caution you not to throw all this in your calculator right now to get like you might like want a number for what's in front of t, or the e to the power of, but it's just gonna, just wait till then if you have to. It'll just save you from rounding error. So I'm going to take the natural log of both sides because this is in the exponent, even though my handwriting is terrible. And I have natural log 0.9 equal to the natural log of e of all this mess. And they cancel each other out. So, this gives me the natural log 0.9 equals to natural log 0.5 over this big number times t. And so I can multiply both sides by this number and divide by this, or I can just multiply both sides by this reciprocal. So I get t is equal to 703800000 over the natural log 0.5 times the natural log 0.9, and if I put that in my calculator, I get t is approximately 106,979,777 years. So that's something like you would do in your chemistry class for sure. And that's the last example I have for this section, but if you want to watch more videos in the PDF, there are these live links. You can come to office hours and see me. I'm always lonely in office hours, or you can definitely send me a Canvas message.